Hello guys, so in this example we're going to go over how we're going to apply the chain rule for partial derivatives. And basically the chain rule from calculus 1 tells us that the derivative of an inside function times the derivative of the outside function will give us its derivative of that particular function. But the chain rule for multivariable functions requires us to use partial derivatives. So basically right here is we have a formula which is the derivative of a function w, which is a function of x, y, and z. So multivariable function will be the derivative of w with respect to x times the partial derivative of x with respect to t plus the partial derivative of w with respect to y times the partial derivative of y with respect to t plus the partial derivative of z of w with respect to z times the partial derivative of z with respect to t. So in essence, when you see this thing that looks like a 2, it's just basically saying it's a partial derivative. D is for regular derivatives, but when you see this little notation that's a 2, it's basically the same thing, but it stands for partial derivative. So right here we have a function of w, which is x squared times y raised to the 6th power minus 4x plus z cubed. And we're asked to find the partial derivative of w with respect to x, y, and z. So we use this formula right here. And notice how we have x is equal to 2t, y is equal to t cubed, z is equal to 20t. So the first thing we're going to do is we're going to go ahead and do this step by step. So w with respect to x, we're going to find the partial derivative of w with respect to y, and we're going to find the partial derivative of w with respect to z. So in doing that, we just take the partial derivative of this w function with respect to each one. If you don't know how to take partial derivatives, I have a video on that, which is very important for multivariable calculus. But without further ado, we're going to take the partial derivative of each. So the partial derivative with respect to x would be 2x times y to the 6 minus 4, and then the partial derivative of that with respect to x is 0. So now the partial derivative with respect to y would be equal to 6 times y to the 5th times x squared, because that's our constant. And that's it for that one, because this is an x term, this is a z term. And the partial derivative with respect to z, this is a 0, that's a constant, 0, that's a constant, and the derivative of z cubed would be 3z squared. So now we've identified these. We've got this step down. So now the next step would be to find the partial derivative with respect to t of each one of these. So basically we're going to find the derivative of these with respect to t. So we're going to find dx over dt. We're going to find dy over dt. And then we're going to find dz over dt. And how do we do that? It's real easy. So we just take the derivative with respect to t of these functions right over here. So we know x is equal to t squared. Y is equal to t cubed. Z is equal to 20t. So now we take the partial derivative of x with respect to t, the partial derivative of y with respect to t, the partial derivative of z with respect to t. And in doing so, whenever we compute these, The partial derivative of x with respect to t would just be taking the derivative of this, so it would be 2t. Partial derivative of this one with respect to t would be 3t squared. For this one, it's 20. Partial derivative of 20t would just be 20. And now the next step is just to plug it into chain rule. Plug into formula. So we have our formula right here. So we have our partial of x with respect to t, y with respect to t, and z with respect to t, as there are these three functions right here. And then we have our partial derivative with respect to x, which is this one right here. Partial derivative with respect to y, which is this one right here. Partial derivative with respect to z, which is this function right here. So now we just group them together. So we just plug it into this formula. So I'm going to go ahead and write these over here as well. So dw over dx, partial w with respect to y, partial w with respect to z. I'm going to put a little line to separate them. So partial w with respect to x would be 2x times y to the 6 minus 4. Partial derivative with respect to y would be 6x squared y 5 times y to the 5th. Partial derivative with respect to z would just be 3z squared. So now we just plug them into the formula. So we multiply these two terms together, add them to these two terms together being multiplied, add them to these two terms together being multiplied. So in doing so, one thing we're going to do is first we're going to just set it up like normal. So we have partial of w is equal to 2x times y to the 6 minus 4 times 2t plus the derivative with respect to y, so these two terms being multiplied. So we get 6x squared times y to the 5th power times 3t squared plus, and put brackets over here, these two terms together being multiplied. So we get 3z squared times 20. So now, before we simplify any further, the next step is to just, all these three values right here that are with respect to t, we're going to plug them in respectively where we see x, y, and z. We're going to plug these terms into here, so that way we have everything in terms of t. Because at the end of the day, we're trying to find the derivative of w with respect to t. So that's what we're going to go ahead and do. So the next step is to plug in x, y, and z into dw over dt. So that way we can have everything in with respect to t. So this thing right here. So we're going to just quickly jot down what our x, y, and z was. So our x was t squared, our y was t cubed, and our z was equal to 20t. So now the next step is to just plug these terms into this, what we were able to come up with here, down here. So there we go. Now we can see the whole formula. So dw over dt is equal to 2 times x. So we substitute x with t squared times y to the 6. So t cubed, but raised to the 6th power. So t cubed raised to the 6th power minus 4 times 2t. 2 and then t. We don't have to plug in anything there because it's not a term of x, y, or z. Then we add this term with our y term. So our y term would be 6x squared would be t squared, but we're squaring it since it's x, times y to the 5th. So it's t cubed, but to the 5th power, times 3t squared, plus, so we're going to simplify this. 3 times 20 is equal to 60, z squared. So 60, then our z squared. What is our z? Our z is equal to 20t, so we're going to square 20. So z squared is equal to 20t squared. We're going to square. So now the next step is literally just to simplify the heck out of this. Which, yeah, it's a lot of simplifying, but we're going to go ahead and do that. So dw over dt is equal to t cubed raised to the 6th. Whenever you have it set up like this, you're going to square this, so it's t to the 18th. But then you multiply it with this one right here, so it's 2 times t squared times t to the 18th. I'll show the simplification in the next step. Minus 4 times 2t, big brackets around this one, plus in our next step we get t squared, so we get 6 times t to the 4th times t to the 3rd raised to the 5th power would be t to the 15th, properties of the exponents, times, I probably could have simplified this to 18, but I'll do it in the next step, times 3t squared, plus 60 times 400t squared. So yeah, a lot of simplification, but we're not even done yet. So we're going to go ahead and simplify this a step further. So whenever you have the same base and you have exponents, you add them together, just properties of the exponents. So this would be equal to 2t to the 20th minus 4 times 2t. So yeah, we are simplifying a little bit further. Plus over here, 6 times 3 is 18. The same base. So t to the 4th times t to the 15th times t squared. Same base, so we can just add all the numbers in the exponent. So this would be t to the 21 power. Yeah, I'm just put a line right there. So that way we can see each step being simplified further. Plus 60 times 400. We have 3 zeros as placeholders, so it would be 24,000 t squared. So furthermore, so dw over dt, sorry. So now our final answer, after all this simplification, we distribute this 2t into here. So we just get 4t to the 21 minus 8t plus 18t to the 21 plus 24,000 t squared. And we can actually still simplify this a little further by combining the 18t to the 21 to the 4t21, which would give us 22t squared. But I'll leave it as this, but just know that you can simplify the 18t squared with the 4t and you'll get 22t squared. But I'm not going to do that. I think I'll leave it like this for now. But that's basically how you take the chain rule applying partial derivatives. So it is actually a lot of simplifying when you have to substitute these terms back into the equation. But in retrospect, we're going to go ahead and go over everything we did because the process is very easy. It's just a lot of simplification. So the first thing we did was we found the partial. So we have this function of w, which is of x, y, and z. We found the partial derivative with respect to x, with respect to y, and with respect to z. We got these functions respectively. Then we did the same thing over here. And notice how I lined them up right next to each other, so that way we can see that this multiplies with this multiplies with this multiplies with this. So then we are given these functions of x, y, and z with respect to t, and we took those partial derivatives. So partial derivative of x with respect to t is this. We took the derivative of this with respect to t, we got this. Derivative of 20t with respect to t, we got 20. Then we plug them into this formula right here. So we multiply the x components, the y components, and the z components. And then we add them together, which is what we did here. And then from there, it's just a lot of algebraic, easy, but a lot of algebraic simplification. And just know you can, I ran out of space, but I'll put the final answer up here. So that way for your reference, the final answer was 24,000 t squared plus 22 t to the 21 minus 8t. So that is actually our official final answer when you simplify the two terms that have the same exponent. But I really hope that was helpful. Thank you for watching. Hello guys, so in this video we're going to go over how to find the chain rule for partial derivatives. And basically we're going to apply the chain rule but for a multivariable function. In Cal 1 you learn how to find the chain rule for a single variable function where you take the derivative of the inside function and multiply by the derivative of the outside function, and that was your derivative. But for multivariable functions you have to take partial derivatives. So without further ado, we're given this super long function. So we're given e raised to the z times y. So yeah, that's a z. Plus x times z squared minus 6x times y to the fourth times e to the fifth. So without further ado, the first step we do is we're going to find, we have this formula right here, so we're going to find these components. So we're going to find the derivative with respect to x, with respect to y, and with respect to z of the function w. So we're going to find dw over dt, or dw over dx, sorry, dw over dy, and we're going to find the derivative of w with respect to z. And notice how I don't use a d, I use a like a 2 looking thing. That's basically just the notation for partial derivatives. So just when you're doing a partial derivative, it looks something along like this. It's not a 2, but it's the symbol for partial derivatives. So without further ado, so the derivative of w, the partial derivative of w with respect to x, partial derivative of w with respect to y, partial derivative of w with respect to z. So in taking these derivatives, so the partial derivative of x, this one's 0 because it has no x terms. This one, however, will just be z squared minus 6y to the fourth times e to the fifth z to the fifth. If you don't know how to take partial derivatives, I do have a video on that, so just go ahead and check it out. I'm just going to go ahead and go through it because I have another video specifically for taking partial derivatives. So now the derivative of with respect to y, so we get e raised to the z times y, so we treat the z as a constant. So the derivative of this would actually be z times e raised to the zy, because we're treating the z as our constant, plus x times z squared would be 2xz minus, oh, this was 0, sorry guys. That's 0, that's not supposed to be there. I was thinking z, but this is with respect to y. But it's good that you can catch yourself making mistakes. So minus 6x times y to the fourth times e to the fifth, so we get 6x times z to the fifth times the derivative of this would be 4y cubed. So now, right here, yeah, ignore that. And now the derivative of w with respect to z. So the derivative of w with respect to z would be y times e raised to the z times y plus, now this would be plus 2xz minus 6x times y to the fourth. Then the derivative of this would be 5z squared. 5z to the fourth power. So now we have our partial derivatives with respect to x, y, and z. So now the next step would be to find the partial derivative of x with respect to t, partial derivative of y with respect to t, partial derivative of z with respect to t. I'll put parentheses to make sure that they're three different things. So we're given these three functions. We're given x is equal to t, y is equal to this number, z is equal to this number. So we're going to go ahead and write those down just so we can have them for our references. So whenever we do find the partial derivative with respect to t, we just take the derivative with respect to t. That's all we're doing here. So the partial derivative of x with respect to t, partial derivative of y with respect to t, partial derivative of z with respect to t. So this right here, the derivative of t with respect to t is just 1. The derivative of this number with respect to t is 0. The derivative of this number with respect to t is also equal to 0. So now we have our numbers. So what I'm going to do is, whatever we had from the last page, I'm just going to bring it back over here just so we can have it for our reference. So dw with respect to dx, the derivative of w with respect to y, the derivative of w with respect to z. So I'm just going to plug in these. I'm going to make them look nicer than what it looks here so we can have for our reference. So z squared minus 6y to the fourth times z to the fifth then we have for the derivative with respect to y is z times e to the z times y minus 6x z to the fifth. I'm going to simplify this right here. 6 and 24, I'm going to simplify it. So minus 24 x y cubed z to the fifth. See if I can fit it all. There we go. And now the derivative with respect to z. So we're going to go ahead and just simplify this. So we have, this one's a longer one, so I'm going to write it down here. So y times e raised to the z times y, because we're treating our, for the derivative with respect to z, we treat our y as our constant. So our y would go down as if it was a regular exponential derivative, plus 2xz minus, and we're going to go ahead and join these terms since they're both constants. So 6 times 5 is 30. 30x times y to the fourth times z to the fourth. So we get x times y to the fourth times z to the fourth. There we go. We'll make it neater as we go down. So now that we have all this set up, the next step is we plug this into a formula. So we plug into a formula. So what's our formula? Our formula is this one right over here. The derivative of w with respect to t is equal to dx over dt times the partial derivative of x with respect to t plus dw over dy times the partial derivative of y with respect to t plus dw over the partial derivative of z times the partial derivative of z with respect to t. So we're simply going to multiply these two together, and these two together. We're going to multiply them, and we're going to add them together. So that's what we're going to go ahead and do in this next step. So I'll get another sheet of paper. So we're going to multiply the partial derivative of, so now that we're plugging them into the formula, the partial derivative of d with respect to t is equal to all this, z squared minus 6y to the 4th times z to the 5th. We're going to multiply this by our dx over dt, which is simply 1. Then we're going to get our y component, so this thing, so dw over dy, so we get z times e to the zy minus 24 times x times y cubed times z to the 5th times our derivative of y over t, which is 0 in this case, plus the derivative of z. So for z, we get all this, so we get y times e to the raised to the z times y plus 2xz minus 30 times x times y to the 4th times z to the 4th. And all this is being multiplied by 0 because this is our dx over dt. So it turns out for this particular problem, we can actually just do a lot of simplification. So I'll draw a line right here. So now the next step is I'm going to simplify this. So dw over dt. We're going to go ahead and simplify this, so we get z squared minus 6y to the 4th times z to the 5th times 1. And it actually turns out this times 0 all goes to 0. So all this goes to 0. All this times 0 all goes to 0. So that makes our job a whole lot easier. But we're not done yet, because we're asked to find the derivative of w with respect to t. So in doing so, what we're going to do is we're going to substitute. So we're going to plug in. We're going to go ahead and plug in y and z. So we can get everything in terms of t. So that's exactly what we're going to do. So I'll just jot them up here what x is. X is equal to t. Y is equal to this number, 1017. Z is equal to 20. So now that we have these values, I'm going to just put them right here in their own little box. These variables, we substitute them into this formula. So dw over dt is equal to z squared. So we get 20 squared minus 6 times y to the 4th. So, oh, that's going to be a big number. Oh, well. Times z to the 5th. Yep, that's going to be a huge number. 20. All this is being multiplied by 1. So, basically now, it's really simple. We just go ahead and we're just going to go ahead and just plug this all in. So dw over dt will actually come out to be a scalar value in this case. So from there on, you just grab your calculator and just plug it all in. I mean, unless you want to try to venture and do it for your head, go ahead and use your calculator. So that number times that number times 6. So I got a very huge number. A very huge but negative number. I got minus 2.05. So I'll round it to 2.1 times negative, by the way, times 10 to the 19th. That's my final answer. But this problem did have a lot of, the hardest part of this problem was taking the partial derivatives, because we did not have a, I guess, a desirable function. We had a very undesirable function. We had e raised to the z times y. So we had to know what the exponential derivative properties were to just treat whichever one we're not deriving for, treat it as a constant. So we took these that are in parentheses, multiplying it by these. And how do we find these? We found these by taking the derivative of x, y, and z. And we did that. And then from there, we just we multiply these two, and then we add them all together. And then we did that over here. So this zeroed out and this zeroed out, and this one just goes to 1. So we simplified all this. There were no t terms in this. It was actually a scalar value, and we got negative 2.1 times 10 to the 19th. And that's how you take the chain rule of for partial derivatives when you have a multivariable function. Thank you for watching. I hope that was helpful.